All right, hello everyone. Welcome back to Physical Geology 1403. Today, I'm not going to sign into OneDrive. Thank you. Today is Lecture 2, Matter and Minerals. How are we all feeling with Lecture 1 content? Pretty comfy? Yeah? Did you think of any questions since the last time we met? For my online students watching this later, this is the right time to leave a comment, go react, leaving whatever questions you have there. As of right now, I'm still trying to figure out how to get OneReact licenses going. For some reason, they're dragging their feet with it. But we'll get there. Let's see. I think as far as class announcements go, I don't really have any except that today you will be receiving your first lab. You're going to be learning here in class today how to do the lab, what information you need to know for the lab. And so by the end of the class, you will be signed. And we might have a little bit of time at the end. This is going to be a little bit of a longer lecture as well because it sets more foundations. Well, you're jumpy today, aren't you? For those of you watching online, by the way, this is Shere Khan. He is a Honduran milk snake. We have a lot of milk snakes here in the U.S. They typically hang in the red and black, maybe the occasional yellowish stripe color range. Honduran ones have beautiful oranges and reds and black stripes and things like that. So kind of looks like a tiger. So we named him after the tiger in the Jungle Book. Anyways, okay. Are we all good? Should we just jump right in? Yeah? All right. So last time we talked about global scale, kind of large scale, a bird's eye view of geology, geosciences. Science in general, really. Today we're going to be kind of diving in on the smaller scale stuff. Here we go. Okay, so that big global perspective that we did last time, we're focusing in on the small scale things, okay? What all the big stuff is made out of, okay? Think of it like that. Camera, stay with me here. Okay? So, what is matter? The correct answer is nothing. What's the matter with you? Come on, it's not too early for a joke on you, right? All right. Matter, though, is stuff. It's what everything is made out of, okay? So, atoms, right? Particles, okay? The fundamental building blocks of everything. That's kind of, matter is a word that we kind of use to describe everything that's made out of something, okay? I'm not going to go into it. There are technically things made out of what we would define as nothing, because it's not matter as we know it, but that goes into dark matter sort of stuff and antimatter, and we're not going into that sort of physics, okay? We're not going that deep into it. As far as you and I are concerned, the balance of this class, matter is matter is matter, and stuff is made out of matter, okay? Now, when I say matter, I'm talking in particular about particles that make atoms. There are three types of particles. Protons, neutrons, electrons. Those three things together make the atoms on our periodic table. Okay, those elements right there. Protons and neutrons combine together to make a nucleus. That nucleus is surrounded by electrons. Sound familiar? We've all learned this before. I assume in my classes, because I only have 8 weeks to teach you guys, I assume that you know the fundamentals of chemistry and physics, okay, the basics. I fly by those. A few of the more important concepts like this, I do talk about. For the most part, I have to assume that you've taken those already because you're in college, okay? All right. Now, electrons differ pretty substantially from protons. They are about 1/2000th the mass of a proton, okay? The smallest of all the particles in your atom. When I say that electrons are circling our nucleus, a lot of the times, the perspective that people have is it looks something like this, okay? Where each electron is kind of zipping around in an orbit, okay? That's how a lot of people describe it, an electron orbital. That kind of gives this perspective, That's not actually what's happening, though. Okay, I want to correct that perspective right now. What's actually happening is think of it more like an electron cloud or shell. Okay, where the electrons are traveling so fast, about 1,360 miles a second. They're traveling so fast that they are essentially making a solid barrier a certain distance away from the nucleus. Now, why is this important? It is those solid electron barriers that bond with other electron barriers in various different ways, and we will talk about that in a little bit. Okay? It's that which gives things solidity. The electron shells in the bonds in my skin are hitting the electron shells and the bonds in this wall. And that's what's interacting. Okay? All right. So, let's talk about our atoms. Atoms have a couple of distinct characteristics. First one is an atomic number. The atomic number is the number on this periodic table. It is the number in the upper right here. Okay? Who can tell me what the atomic number represents? You said that? All right. Protons. The number of protons in your nucleus. Yes. The number of protons in your nucleus is what determines which element it is. You change the number of protons, you change the element. All right? Great. So you can see here on this one, it's in the middle. Over there, it's on the right. It just depends on who organized it. There are, as of now, 94 natural and 24 synthesized elements on the periodic table. What's the difference between a natural and a synthesized element? Why does it matter? Get it? Matter. Okay. What does natural and synthesized mean? It's an easy one to warm up on.
One's natural, one's made by humans.
What does natural mean? Anyone want to help him out here? What does natural mean? Ivani, is your hair color natural?
No.
What does that mean? Yeah, something inherent to something, okay? So, natural hair color and unnatural hair color, dyed hair color, are not the same. Natural and synthesized. Something that is naturally occurring, something that we have to cause to occur. That's what synthesized means. How do we synthesize elements? You guys ever heard of a particle accelerator? You know what that is? What, you don't have one in your kitchen? What? No. These are massive, multi-billion-dollar machines that often will span miles in length, because what you do is you super-energize a particle, collide it with another particle at extraordinarily fast speeds, like near speed of light speeds, and then it creates a whole bunch of byproducts. Some of those byproducts are synthetic elements, even if they only exist for a picosecond. They still existed, and therefore they go on the periodic table of elements. That's what these are talking about. Man-made elements using our technology and the ways that we figured out how to manipulate naturally occurring elements. Okay? So that's what these are. All right, so in your nucleus, protons have a positive electric charge. Electrons have a negative electric charge. What do you think neutrons have? Yeah, they're neutral, hence the name neutron, right? Okay. Good. Our periodic table is organized by a couple of different properties. Okay? First of all, notice 1, 2, 3, 4, 5, 6, 7, 8, 9. They're in numerical order, left to right. That numerical order following what trait? What are the 1, 2, 3, 4? What do they represent? protons in the nucleus. Yes. Okay, so we have it organized initially by the number of protons in the nucleus. Okay, great. We'll talk about those other properties here in a second. Okay. Now, let's take a minute to talk about bonds. Okay? What is a bond? If I were to say that I bond something to another something, what does that mean? Sarah, say that louder. Made them one? Yeah, you could think of it like that. It's not that they're becoming one object. They are combining to make a new whole. Whole with a W, right? W-H-O-L-E. Okay? They are making a new whole. Okay? They are combining for however long to make something new. That's what a bond is. What dictates how long a bond lasts? Well, often it's the external factors. How much heat, how much pressure, right? Maybe I use heat and pressure to make a bond. Maybe I can use heat and pressure to break a bond. Okay? There are several different types of bonds you're going to learn about. Ionic bonds, covalent bonds, and metallic bonds. In general, it is a more stable condition for atoms to be bonded together than for them to be separate, which is why we are surrounded by bonds. Okay? Bonds happen all the time. I'm sure that's very comfortable for him, but my arm's getting tired. Okay, so let's talk about how this happens. There's something called the octet rule. You guys heard of this before? The octet rule basically states that atoms tend to lose, gain, or share electrons until they have 8 electrons in their valence shell. Valence shell meaning the outermost shell. Most elements have more than 1 electron shell. And so, to get 8 electrons in that outermost shell, you usually need a bond with something. And this, my friends, is the other way that we organize the periodic table. Woo, I got you. Notice we have not just the numbers, they're not just organized by numbers, they're also organized in columns. Look at this. 1, 2. We're going to skip these. There's a reason why these are down here like this. We'll talk about that in a minute. 3, 4, 5, 6, 7, 8. Coincidence? No, you organized it like this intentionally. Why? Every one of these elements that is in column 1 has 1 valence electron. Every one of these in the second column has 2 valence electrons. We're going to skip over the metals for now for reasons. Okay, 3. What's in column 3? How many valence electrons do they have? 3. How many do they want? How many do all of them want? 8. 8. Exactly. So, everything in column 1 wants 7. Everything in column 2 wants 6. So on and so forth. You want to hang out up here for a little bit? That'll work. Okay. It's probably going to go down my shirt because it's warm, but that's all right. All right. So, here it is. This works all the way up until when? Nope, I knew it. You were about to fall down, weren't you? Knock it off. This works all the way up until when? What column do we eventually get to where this won't work? Column 8. Column 8 will have how many valence electrons? 8. How many does it want? 0. And that is why we have these all over here. Helium, neon, argon, krypton, xenon, radon. These are collectively called noble gases. They are inert because they do not typically bond to anything else. When there's something particularly volatile, like an explosive or electronics that we want to keep very secure, we store them in noble gases because we can trust those gases not to mess with the thing. There won't be any chemical reactions that cause an explosion or that ruin our sensitive electronics. Okay? Noble gases. Column 8, 8 valence electrons. Octet rule does not apply to them. They're already happy. They won't bond. Cool with that? All right. So, in a chemical bond, electrons can be transferred, shared, anything like that. Okay? So, when an electron is transferred, it's called a valent or ionic bond. When one is shared, it's a covalent bond. And when all electrons among a given substance, a uniform given substance, are shared, we call that a metallic bond. So let's start off with ionic bonds. So with an ionic bond, you have a positive and a negatively charged ion. Positives and negatives are drawn towards each other, right? That's how magnets work. That's how these work too. That's how these ions work too. Opposites attract. Just like that, I saved you tons of time and money in relationship therapy. Okay? All right. Opposites do, in fact, attract. So what do we have? A positive is drawn to a negative. Here we have a sodium with one valence electron. How do I know it has one? Which column is it in? Look, there it is. Column 1. Then I have a chlorine. Which column is chlorine in? 7. So it has 7 valence electrons. How many does sodium want? 7. How many does chlorine want? 1. Match made in heaven. Okay? And so, we often do see this bond. What do we call the resultant of sodium bonding with chlorine? Sodium chloride, aka salt. Extremely common bond that we see on our world. One that you and I rely on. Without salt, we die, as does pretty much everything else that lives on this planet. Okay? We have grown chemically through time to be reliant on this extremely common bond. Okay? This is a very easy example of how to understand an ionic bond. As a result of the sodium transferring its one valence electron to the chlorine is now happy, and the sodium gets the pleasure of staying attached to it. Okay, so both are happy in that bond. All right? But now our sodium is a positive ion, and our chlorine is a negative ion. Why? Why would our sodium now become the positive ion? What did it lose? An electron. And what charge does an electron have?
Negative.
Negative. So by losing one of my negative particles, I become net positive. The chlorine, what did it gain? An electron. What charge does it have?
Negative.
Negative. So by having an additional negative particle, it has become net negative. And there we have our positive and negative ions in this ionic bond. Okay? Octet rule brought them together. Their differences kept them together. Okay? That's how it works. I know, so cheesy, right? All right. I should write romance novels, right? Okay. Now a covalent bond. A covalent bond is when electrons are shared between two particles, between two atoms. A simple example of this is hydrogen. A hydrogen on its own just has that electron shell, the one electron shell. But when two hydrogen atoms approach each other, the electrons in the shells of each are equally drawn to the nuclei of the other. And so what you end up with is electrons zipping back and forth between both nuclei. And this is how you get H2, otherwise known as hydrogen gas. Extremely flammable. Okay. All right, so that is your covalent bond. The electrons are shared. Now, metallic bonds. With a metallic bond, all of the electrons in that substance are shared, equally distributed, can freely transfer from anywhere to anywhere else. This gives metals a very unique use case. What do we call them? Not magnetism. It's another fantastic conductivity. Bingo! This is why metals are conductors. This is why they have their very own separate section down here. Because through metallic bonds, they can freely share those valence electrons with each other, and that allows any electrons to pass freely through the substance. Some are more conductive than others. Silver and gold, fantastic conductors, right? The other ones are too. Copper is a fantastic conductor, just not as great as silver or gold, right? Matter of fact, most silver and gold and copper that we have in our world that we produce is used as a conductor, okay? Yeah, I think that we understand the three bonds well enough. Do I need to go over anything else here? Okay, all right. Now, I told you about the mass or the atomic number, the number of protons you got. I told you about octet rule, the number of electrons in the outer shell that dictate what elements want to bond with what, right? There's something else. So we talked about the protons. We talked about the electrons. What have we not talked about yet? Huh? What's our third particle? Huh? The metal ones? Well, we just talked about the metal ones. I'm talking about which of the three particles in my atom have we not really talked about? Neutrons. Is that what you said?
No.
No, okay. I was making sure I didn't mishear you. Okay, yeah, we haven't talked about the neutrons. The neutrons, they live in the nucleus. We haven't talked about their role yet. Let's do it. Let's talk about atomic mass. What is mass? It's a different measure than volume. Volume and mass make density, which we've already talked about. So they do work together in measurements. What is mass itself? Say that louder. The total amount of protons, neutrons, and, if you're being very precise, electrons in a given substance. Yes. Otherwise, how much stuff is in it? How much matter is in my thing? Each of you has a mass. Did you know that? Except we don't typically refer to it as mass here unless you're being very scientific. What do we call that usually here? What's pounds a measurement of? Weight. Pounds are a measurement of weight, not mass. When you were measuring mass, we'll usually do it in grams or kilograms. Weight was usually measured in pounds, tons, things like that. What's the difference between mass and weight? Why don't I say atomic weight instead of atomic mass? What? No, you don't need to look away.
Yeah, I'm just thinking.
Okay. Feel free to think out loud. This is a safe place. I'm not going to make fun of anyone. Okay? I deeply value that you are all here. Let's make this a conversation. What is the difference between mass and weight? I'll give you a hint. Weight on Earth is different than weight on the moon. However much you weigh here, you weigh less there. There's a clue. Why? What is the factor that would make that true? Say it louder.
Gravity.
Louder. Gravity. Yes, I agree too. I just wanted the room to hear you. Okay? It's gravity. Yes, gravity. Oh, look, you made a bracelet. Okay. Gravity. Gravity plus mass equals weight. My mass, if I were to snap my fingers and instantly appear on the moon, I would die. But my mass would stay the same. My weight would change. Okay? Mass is the total amount of every particle in my body right now in this moment. Weight is mass plus the gravitational pull of the Earth. When I'm on the moon, the gravity of the moon is different. And so my mass is going to stay the same, and therefore my weight changes. Okay? So, to be scientifically accurate, we don't say atomic weight, because that is not something that we can translate anywhere else in the universe. Atomic mass is, though. Okay? All right, just so we're clear on that. So, atomic mass includes protons and neutrons, and, being very precise, the mass of your electrons as well. But remember, an electron is 1/2000th the mass of a proton. Most elements, most periodic tables, I was going to say scales, it's not a scale. Most periodic tables will not tell you what the mass is, including the electrons. This one does, which is why some of the numbers go real far out, right? Like, cancel them. 180 plus 9.94788, right? So it's, some of them can be real precise like that, but not all of them will. Okay? So why does mass matter here? Well, when you change the number of protons in your element, what do you get? Are we feeling sleepy this morning? It's understandable, first week of school. Do you need a joke? If I tell you a joke, you guys, yeah? You really want a joke? All right. Why didn't the T-Rex sell rifles? Because he only has small arms. Was that good enough? All right. So, what happens when you change the number of protons in your element? What do you get? Cameron, stay with me here.
A new element?
Ah, there it is, a new element. Because the difference between the elements is dictated by the number of protons in the nucleus. Boom. Change the number of protons, get a new element. Okay, now what happens when you change the number of electrons in your valence shell? I mean, you say that you keep the same element, but what does it become? Huh?
One.
No. It can form bonds, and this can happen as a result of bonds, but there's a word for what we call it. When you gain an electron, what does your charge become? Negative. When you lose an electron, what does your charge become? Positive. What do we call those? They have become ions, right? Positive or negatively charged atoms are called ions. So, change your protons, get a different element. Change your electrons, get an ion. What happens when you change your neutrons? We haven't talked about that yet. Let's talk about it. When you change your your neutrons, you get an isotope. You heard that word before? An isotope is what you get when you mess with the atomic mass of an atom without changing its protons. Okay? So, let's look at carbon as an example. Where is carbon on my periodic table of elements? Right there. Fourth column. How many protons? 6. But what is its atomic mass? 12. Therefore, how many neutrons must be in its nucleus? If its total mass is 12, and 6 of those 12 are protons, then how many of those must be neutrons? 6. 6 plus 6 is 12, right? Total mass 12, 6 of it are protons, 6 must be neutrons. Okay, that's what our normal plain Jane carbon looks like. We call it carbon-12 when we're discussing isotopes. There are isotopes of carbon called carbon-13 and carbon-14. What's changed to make an isotope of carbon-13? The normal version is carbon-12. What has changed to make carbon-13? Say that again? Not an electron. That would make it an ion. Huh? If we change the number of protons, we get a different element. The number of neutrons. Specifically, what has changed in the number of neutrons in my nucleus? to go from carbon 12 to carbon 13, I got an extra neutron somewhere. This happens fairly often. Carbon 13 is a very common isotope in our world. Okay? Carbon 14, what's happened? Say it louder. I got 2 extra neutrons in my nucleus. That one's significantly rarer. As a matter of fact, carbon 14 is an isotope that we only see from the result of burning fossil fuels. This is the isotope that we've used to track exactly how much carbon dioxide we've put in the air since the Industrial Revolution. Because only carbon 14 would be coming from fossil fuels. Okay? So when you look at a diagram of carbon dioxide released into the atmosphere, since the 1700s, it looks like a hockey stick, like an exponential curve upward. And it's not just like total carbon, that's carbon 14. That's how we track it. Okay? So these are isotopes. Okay? Now studying isotopes clearly has use. I just told you one use case, atmospheric studies. We can also use the same thing in plants. We can also use the same thing in animals. Remember I told you last time my master's thesis was an isotope analysis of fossils to reconstruct a paleoclimate of the Ice Age Oregon. Ice Age Oregon. Yeah, I used isotopes in fossils to do that. Carbon 13, carbon 12, oxygen 16, and oxygen 18 isotopes. Okay? Once you know why they show up, where they can be found, and what different concentrations of them mean, isotopes open up a whole new world of study in science. It's fascinating. Not all of them are benign, though. Oxygen 16, oxygen 18, carbon 12, carbon 13, they're kind of like, it's whatever. We're chill. We can have a few extra neutrons. Some of them don't like it. You add neutrons, you take neutrons, they fall apart. They're just like, I don't want to be like this anymore. An example, uranium. Where is uranium on my periodic table of elements? 92. Boom. 92 being how many protons it has. What's its mass? 238. Boom. 238 total mass units, 92 of which are protons. However, if I change the number of neutrons in there, it is no longer stable. It becomes what we call an unstable isotope. They fall apart. They will blast particles off of themselves, electrons, neutrons, even protons, in an attempt to reach a new stable state. And this, my friends, is where I introduce you to a very important concept in nature. In general, all things in nature are seeking a state of stability. If that were not true, unstable isotopes would just stay unstable. Nature likes stability. This is going to be a concept that comes up fairly often. I'll bring it up over and over. Here's your first example. Unstable isotopes will blast particles off of themselves until they reach a new stable condition, what we call a daughter isotope. Okay, so your parent isotope is what you start with. Daughter isotope is what you end up with. For example, uranium. Uranium-238, when you remove a couple of neutrons, you get uranium-236. Uranium-236 is what we use in nuclear reactors. It is the fuel for nuclear reactors. Okay? Why does it work in a nuclear reactor? Remember those particles I just mentioned that fly off of it? You know what we call those particles? Radiation. Highly energized particles flying away from some sort of atomic reaction. That's radiation. Okay? So if you go to a nuclear reactor and you open the reactor door, you get bombarded, you die. Why? What does radiation do? Super highly energized particles running into your cells rips them apart. That's why people die from nuclear accidents. Okay? That's why when a nuclear reactor breaks down in an earthquake, like what happened in Fukushima a few years ago, right? In Japan. What happened in Chernobyl, okay? Decades ago. 3 Mile Island. Any of these nuclear reactor incidents have resulted in deaths. It's because that radiation gets released and it literally tears apart your cells. Okay? Now, It's extremely useful because if we can contain it, all that energy, oh man, that can make electricity. In a nuclear reactor, what you do is you have a vessel capable of containing all that radiation and using it to heat something up, usually water. You use it to heat up water, the water turns to steam. You channel that steam into a turbine, it turns the turbine's attached to magnets, the magnets generate electricity as they rotate. And that's how nuclear reactors make electricity. Very, very useful, very efficient, fantastic. I firmly believe that if there is ever a path for our society past fossil fuels will keep us sustained for a while, but eventually it is a non-renewable resource. At least it renews over millions of years, but that won't do us any good. If we are ever to move past that, which eventually we will need to, because it will eventually reach a point where our consumption drastically overwhelms our production, it's going to be nuclear. Because solar, wind, none of that matches up to the energy that we need. It works for small scale stuff, not national levels of need. Nuclear, I think that's a good go. Now, there is another way to use the fact of these unstable isotopes. Okay? This one. Nuclear weapons. The first nuclear weapons were made out of uranium-235. 236 is just unstable enough that you can put it in a reactor and trust that it will generate enough radiation to do what you need. Uranium-235 is so unstable that all you need is to give it a little more of an energetic push, and all of a sudden, it starts ripping itself apart, releasing all of the quantum energy tied up within its bonds. Okay? All that energy. And that's what makes a weapon. It literally lights the atmosphere on fire with the heat. The radiation is devastating. I used to live in Japan. I lived there for 4 years. I visited both Nagasaki and Hiroshima. Do you know what those cities are significant for? Those were where the 2 bombs were dropped, Fat Man and Little Boy, and World War II in the Pacific. Okay? As soon as those bombs were dropped, the Japanese Empire pretty much surrendered. Because they were like, oh, can't fight that. Annihilated 2 cities. The craters are still there. They have museums built there to remember what happened. It is an event, an act that was so absolutely stunningly devastating to an entire empire that it has shocked them for generations and will continue to. It shocked the world to the point where after those bombs were used, the nations came together and said, hey guys, we can't ever do that again. And so there are nuclear accords to prevent that from happening, at least not without sufficient provocation. Naturally, every country that could started producing nuclear weapons. And bigger ones. Do you know what the largest nuclear weapon ever exploded was? Say it louder. I think you said it. Tsar Bomba. Yes, the Tsar Bomba. Set off by the Russians. The Russians blew it up on this vaguely banana-shaped island right there. The upper half of that island was uninhabitable. You can go on Google Maps, you can go on a satellite view and look at that island, and you'll still see a crater the size of a small city. It was an eruption, or not an eruption, it was an explosion so powerful, it shattered windows in Europe and was felt by earthquake devices across the entire planet. Can't hide that. As soon as they set that off, the rest of the world knew what happened. And then they came together and said, okay, this kind of weapon, it's a hydrogen bomb, by the way, this kind of weapon cannot ever happen. It would take about 2 to 3 dozen conventional nuclear weapons, like what was used on Japan, to reduce society back to where we were pre-industrial revolution. It would only take 5 or 6 hydrogen bombs in the right place. You take out the capitals plus the industrial centers of the 3 biggest countries in the world, and then all of a sudden, everyone else within a few decades, we're all going to be down there. Is US, China, probably one in Southeast Asia, maybe one in Russia, one in 1 or 2 in Europe. Give it 20 years, we're all down there, okay? Because we rely on each other, and the industrial foundations in each nation is kind of intertwined with itself, with each other, okay? So, I know it's pretty dark, but this is the science for why it works. All you need is a little bit of fissile material, the unstable isotope, like uranium-235, and then you need an explosive, usually TNT or some other high explosive. You put a detonator on it, kaboom, you have a nuke. Everyone knows how to do it now. I mean, this is probably, I don't know if I should say this on a video that's going to come on YouTube, but I know how to build one if I could get my hands on the right material. If it wasn't illegal for me to get uranium-235, I could build one in my garage, right? Which is where you get, terrorism and stuff like that. That's why it's highly regulated. The bombs that they dropped in Japan only used, get this, less than 1% of the uranium that they put in there. Yeah. If 100% of the uranium had been used, both bombs would have taken out half the country. Okay? Luckily, at that point in time, the technology wasn't enough to make that happen yet. They put way more nuclear material in there than they needed. But they didn't know how to activate all of it, which is lucky. Okay. Any questions about isotopes, radiation, unstable, stable isotopes, anything like that? The thing about isotopes that's really useful for you and me as a use case here is the fact that they do break down. Remember how I mentioned they go from a parent isotope to a daughter isotope? That happens over a very specific amount of time, a universal amount of time. This is so cool, okay? We define the amount of time that an unstable isotope takes to break down into a stable daughter isotope as what's called a half-life. We do this by saying, okay, of this total amount, let's say I have a dinner plate full of uranium-235, okay? The amount of time it takes for half of that to become lead-207, which is its stable daughter isotope, it's about 53 million years. Sorry, 253 million years, okay? So after 253 million years, half of that dinner plate will be lead, half will still be uranium. Why do I do half-lives? Why don't I measure how much time it takes for the entire thing to break down? Any guesses? Carissa, how many times can I cut something in half before I run out?
Like 12 times, maybe?
12? Okay. Well, I cut it in half 12 times. Am I still left with something?
Yeah.
Can I cut that in half again? Yeah. So how many times can I cut something in half before I run out?
A lot of times.
Never. I'm sure you've all heard you can only fold a paper X amount of times, right? Fold in half X amount of times. True, but how many times can you cut something in half before you run out? Never. It just keeps going, okay? Now I guess eventually I'm going to get down to 2 atoms, and then I cut them apart, and I'm left with 1 atom. How can I split an atom? Oh, I'm going to blow myself up. Right. Sorry, too soon. But up to that point, you can never run out of cutting something in half. So we go in half-lives because that does not give us a cap on how far back we can measure how long this process goes. So 253 million years is a half-life here. Cut it in half again. I have 1/4 of my original amount, but 2 half-lives have passed. Cut it in half again, I have 1/8 of my original amount, but 3 half-lives have passed. Why is this useful? Because as long as I know how long each half-life is, I can measure how much of any substance has that material. So if I'm looking at a rock, and I look at its isotope values, which we do have instruments that do that, and I see it has X amount of, let's say it's got 75% uranium-235, or lead-207, and 25% uranium-235, I know exactly how old that thing is, because 2 uranium-235 half-lives have passed. Does that make sense? This is called radiometric dating. You may have heard it described as another term, carbon dating. Have you heard that one? Carbon dating is actually inaccurate. Carbon dating only actually goes back about 10,000 years. Radiometric dating goes back billions. This is how we are, among other ways, we are able to estimate how old not only the Earth is, but the universe by measuring how many half-lives of these isotopes have passed. And because it's universal, the half-life of uranium-235 on Earth is the half-life of uranium-235 on a planet on the other side of the universe. We are able to use that as a constant. Isn't that awesome? Science we learn here helps us understand out there. Again. Okay. Talked about that enough. So now that we understand the concept of matter and bonds and atoms and elements and isotopes and ions and everything like that, let's talk about how that relates directly to geology. Minerals. Okay, when my bonds form together, they are going to make certain things. Some of those things are going to be minerals. There is actually a specific definition for a mineral that you need to know. I mentioned there are only a few things you need to know word for word. This is the next one. Okay, the definition of a mineral that I give you right now is not going to be the same that you find online, but I have it as this definition for a very specific reason. Okay, every single word in this definition is important, so don't change it. Write it down word for word here. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. That is the definition of a mineral. I'll say it again. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Let's break that down. Naturally occurring. Did we make it? No, it has to happen in nature. Inorganic. Can't be a living thing. Okay? Solid. Can I have a liquid mineral? Not according to geological terminology. Healthcare minerals, that's a totally different thing. If your nurse tells you, hey, you need to add more minerals to your diet, they probably aren't saying eat rocks, right? They're probably telling you to take a supplement. That's a totally different thing. In the mining industry or the petroleum industry, a mineral is anything they can economically remove from the ground, right? So oil to them is a mineral, but not to us because it is a liquid. Okay? To you and me, only solids. Any naturally occurring inorganic solid that possesses what? Orderly crystalline structure. Yes, it needs to have a crystalline structure. We'll talk more about exactly what that means here in a little bit. And can be represented by a chemical formula. We gotta know what it's made of. We gotta be able to communicate what it's made of, and it has to be made out of that thing constantly. This is why we have different minerals, because different minerals will be made out of different atoms, constructed in different bonds to make different crystalline structures. All right? So that is your definition of a mineral. So what's the difference between a mineral and a rock then? A mineral is this definition. A rock is a bunch of minerals together. You've probably heard those words used interchangeably. Use them interchangeably in the past. You pick this up. Oh, it's a mineral. Oh, it's a rock. You've never really noticed or cared what the difference between the two is. No longer, my friends. Now you know the difference. It would be like if I came up to Annabelle with a handful of flour and I said, would you like a chocolate chip cookie? No? Okay. Wait, why'd you say no? I'm trying to give you a chocolate chip cookie, right? It's only flour. So if I pick up this chunk of quartz, which is a mineral, and I say, look at that rock. That's the same thing. Right? It is one ingredient of a cookie. You know what I mean, right? Okay. So, the properties of minerals, and these are what you're going to need to become familiar with for your lab, okay? All minerals have properties. A property is a unique characteristic about a thing. Each of you has properties: eye color, hair color, fashion preference. Okay? There are things that differentiate you from everyone else in this room and everyone else on this planet. You are different than anyone else is. Okay? From the atoms that make you to the things that live inside you. Okay? By the way, you remember I told you about the nebular theory last time? About how every element that isn't hydrogen was made in a star at some point? That includes every element inside of you. Every single component of your body was made inside of a star at one point or another. Pretty cool to think of that. And the exact ratio of those things made in stars billions of years ago is different to you than it is to anyone else. Do you guys know that you have tiny little microbes living inside your stomach? We call them archaea. Microbiota, they're also called. They live in your intestinal tract. It's what digests your food. Did you think you did that yourself? Oh, the pride. No. You have tiny little animals that live inside of your gut that digest everything for you. It's a symbiotic relationship. We get the nutrients, they get the extra stuff. Okay? I know this is typically not something that polite conversation talks about, but we're scientists. That's where flatulence comes from. The gas that you expel is the byproduct of your microbiota breaking down that material. You want to hear a fascinating statistic? 1 centimeter of your intestine contains more individual living things than the entirety of all humans who have ever lived. Yeah, that's how many of those are inside of you digesting your food at any given time. You go to the store and you look at this. Oh, look, a probiotic drink. What does that mean? You drink it, it keeps those things healthy because they can die. And when they die, you start having gastrointestinal issues, right? Probiotics, prebiotics, those are all meant to encourage the health of your microbiome. Okay, I kind of got off track there. I go on more tangents than the math class does across the hall. Okay, so just remember that. All right, so these properties, things like optical properties, namely, how does light interact with my mineral? On the surface or through the structure. Okay. Shape, also known as form, also known as habit. All three of those words describe the natural shape that it grows into. And yes, they do grow into these neat geometric shapes. You'll see some of those. Strength, that is, how hard is it to scratch it? Okay. For your lab, I give you each a piece of glass. And with that piece of glass, you will scratch the mineral or scratch the glass with the mineral. And that gives you a baseline to work off of. Density, taste, texture, smell, all of those are relevant to magnetism. Not all of your minerals will have reactions like that. Okay? Some will have a unique taste. Please, if you're going to taste the minerals, you can feel free to do that to all of them, except 18 and 37 in the back. All of those boxes back there, those are those correspond to some of the materials I've given you to help with the labs. You will be using those as a reference point. Boxes 18 and 37 are toxic. Please do not taste those. If you touch them, wash your hands afterward. Okay. 18 is a lead sulfide, and 37 is an arsenic sulfide. So let's avoid a trip to any emergency rooms. Okay. Some are going to be magnetic. In your test kits, you have little magnets to test that. Effervescence. Some of them are going to effervesce. What does that mean? You're going to put a little bit of acid on them. That acid is going to make some of them bubble up like this, and that'll be a dead giveaway for which one it is. So each one of these minerals has a unique set of properties that you're going to learn to identify. They are the most common minerals on our planet. Okay, ones that you will absolutely run to on almost a daily basis. Whether or not you test for them, it's up to you. You run around dropping acid on every rock you see, I'm not going to stop you. But you're going to learn how to identify them anyway. Okay? All right. And by the way, the acid I gave you guys is very dilute. You don't need to be freaked out by the fact that I'm giving you acid. It's hydrochloric acid, so it's not terribly caustic anyway. and I dilute it quite a bit. If you get some on your hands will feel a little slippery. That's only because it's dissolving the outer layers of skin, which are dead anyway, so you don't need them. Okay? You just kind of like wash your hands and you'll be fine. But do not get it on your clothes. It will dissolve your clothes. Okay? Not immediately, but you will end up with holes in your shirt. I can't tell you how many shirts and pants I've lost to hydrochloric acid. It is my wife's bane. Okay? She's like, another shirt. I'm sorry. I was demonstrating. Okay. So let's talk about each one of these properties individually. Optical properties. This includes things like luster. Luster is a description of how the light interacts with the outer surface of your mineral. Examples of luster could be, this is metallic. This is glassy. Another word for glassy is vitreous, by the way. You'll see that in the literature and in some of the materials I give you. Okay? It looks oily. It looks greasy. It looks like dirt, right? It looks like a lot of things. And how can we observe that? Because of the way that the light is interacting with the outer surface. Okay? Then there is the optical property of light transmission. Okay? So, does light pass through it perfectly? Can I see an image on the other side of this mineral? We call that transparent. It's like glass. Then there is light goes through it, but I cannot see an image. That is translucent. Then there is opaque, which means that neither light or an image can be seen through that material. Okay? So if you think of glass as transparent, my water bottle is translucent, and this cloth is opaque. Okay? Just as quick examples of it. And then there's color. Please be very, very careful when it comes to labs and describing color. Color is not a primary identifier. We do make note of it. It can be helpful as, like, say, a tiebreaker. But color is variable. I can have two minerals of the exact same type that are different colors. Or I can have two minerals that are wildly different from each other but share the same color. So if you look at a mineral and your instant judgment is, well, it's this color, so it must be this thing, you're already doing the lab wrong. Okay? Don't just make a snap assumption, assuming you know what it is based on a few observations. You need to make all the observations. And if you make all the observations, you will find the right answer. Okay? Streak. In your test kits, each of you will have a white and black ceramic plate. That plate, you're going to scratch the minerals on. If your mineral is softer than that plate, it's going to leave behind a color. Either on the black one or the white one. You'll be able to see a color there. Okay? You will make note of that color, that is streak. Basically what you're doing is, because air and water may have changed the color on the outside of your mineral, you're taking just a couple of atoms thick layer of that mineral to see what that color would be. Okay? So, for example, in this picture, this one looks golden, but its streak is black. Okay? All right. Crystal shape, also known as form, also known as habit. Okay? This is the natural shape it grows into. As my chemical bonds are forming, making this mineral, and at the microscopic scale, they are going to keep piling onto each other, replicating over and over in larger form what the geometric shape of those atomic bonds is. And eventually, you're going to get something visible enough to see. For example, you might end up with octahedrons. These magnetite pieces are in naturally occurring octahedral shapes. Why? Because that's what the internal atomic structure looks like. And it's just grown on itself large enough to be visible now. Okay? Dodecahedrons, 12-sided shapes. These garnets grew into that. They were not cut to look like that. That is what they look like by themselves. Okay? So the unbroken shape of your mineral. Halite is cubes. Halite, by the way, mineral name for salt. That is salt. Salt cubes occur naturally. There isn't someone at a salt factory that's just cutting them all into tiny little cute cubes. Okay? They grow like that. Okay. The next property is tenacity. This is how my mineral responds to breaking. Does it shatter? I'm going to call that a brittle tenacity. Does it bend but not retain its shape? Does it snap back to its original shape? That would be elastic, like a rubber band. Is it malleable, like gold or Play-Doh, where I can squeeze it and squish it and exert pressure on it, and it'll keep the shape, right? These are descriptions of tenacity. Now, do not break my minerals, please. Observe the way that it looks like they already broke. Some of them you can put a little stress on, it'll be fine, but please don't bring a hammer to class and go pounding away crazily, okay? I don't have such a crazy budget that I can replace every mineral in the class every single year. All right. Then there's hardness. For hardness, that's the resistance of the mineral to scratching. So you're going to be using glass. We use Mohs scale of hardness to determine this, by the way. It's a scale 1 through 10. 1 being the softest mineral that we know of, talc. This is what we crush up to make baby powder out of, okay? Then, the hardest mineral that we know about, diamond. Okay, right up there at 10. So from 1 to 10, with everything falling in between. And there's a couple of household items here that we use to test things. Your fingernails are a 2.5. Each of you has a penny in the test kit. That's a 3.5. You can use that for reference as well. The glass I give you, though, that's a 5.5. It falls right at the middle. Okay? It's right there at the middle. So when you're doing your lab and you come to the hardness section, you're going to scratch your mineral on the glass. With only the one frame of reference of glass, all you can tell me about the hardness of a mineral is it is either greater than or less than 5.5. I don't need a number 1 through 10. I don't need you to guess. Just say if it's greater than or less than 5.5. Okay? Then there's cleavage. Now, I'm not going to lie to you. Cleavage is the mineral property that people tend to struggle the most with. So, to help, I 3D print a lot of stuff, by the way. I have my own small 3D printing business. But a few years back, because, hello camera, focus on me. Because there was nothing like this, I took it upon myself to design cleavage models, and I embedded magnets in them. So hopefully this makes things a little easier. I actually have a patent outstanding at this at the patent office, but no one's gotten around to approving it yet. So hopefully someone does eventually. But I'm going to describe to you what cleavage is. Cleavage is the manner in which your mineral will break based upon its internal atomic structure. What does that mean? Remember how I told you that all minerals are made out of those atomic bonds? Not all bonds are equally strong. The bond between element 1 and element 2 may be stronger than the bond between element 2 and element 3. When that happens and I exert stress on those bonds, which one's going to break first? Huh? The weaker one. Bingo. The weaker bonds break first. And because a mineral is nothing but a repeating pattern of the same chemical sequence, it's going to break along the weak bonds in the same direction throughout the entire mineral. So, how do we describe this? To describe cleavage, you need to tell me how many directions of cleavage you observe. And when there's more than one, we need to start describing at what angles approximately they meet. I don't need you to whip out a protractor and measure it. All you got to do is tell me if it's at 90 degrees or not at 90 degrees. That's all you got to do. Okay? So now I'll give you some examples of cleavage. This is what one plane of cleavage looks like. If you want to behave. My TA is misbehaving here. Okay. It just splits apart like this, like the pages of a book. That is one plane of cleavage. Okay? Pass these around. Some of them have fallen apart over the years. Some of the magnets have come apart, so just bear that in mind while I'm passing these around. Then you've got two planes of cleavage at 90 degrees. It's basically just going to make a sort of shape like this. Kind of looks like a rectangle. Where you got one plane, case in point, right there, it fell off. It's down there. One plane and two planes that meet, the cleavage planes meet at 90 degrees. This surface over here could be jagged. This surface over here could be jagged. These two flat surfaces where it's clearly broken and is continuing to break along those flat surfaces, obviously cleavage planes. I'm going to take a moment here to point something out. If the cleavage planes are flat, then how am I supposed to tell them apart from crystal form, aka the original shape of the mineral? It's going to be obvious most of the time when your mineral is broken. If it's not obvious to you, it should be obvious to someone else, which is why I encourage you to work in groups for labs. Okay? Just remember your crystal form, the unbroken shape of your mineral. Its original shape. Cleavage planes, broken surfaces that are flat because they are cleavage. Okay? All right. Next, we've got two planes not at 90 degrees. Okay, so two flat surfaces, boom, boom. But they don't meet at 90 degrees. We've got an acute angle and an obtuse angle on this mineral here. Okay. Next up, three planes of cleavage at 90 degrees. All right, it's just a box. Now this is where I'm going to address a question that some of you have probably had already. I said that this has three planes of cleavage, right? How many sides does it have? 6. Professor Hart, how can you say this only has 3 planes of cleavage, which you told us are flat surfaces, when it has clearly 6 flat sides? It's a fair question. Well done, students. Okay, this is why. There are 3 planes, boom, 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 and they're parallel sides. So when I say that this has 3 planes of cleavage, what I mean is, boom, boom, boom. This side is parallel to that plane. This side, parallel to that plane. This side, parallel to that plane. There are only 3 unique planes of cleavage on this box, though there are 6 sides, because 3 of them are just copies of the other 3. But just on different sides of the mineral. So pay attention to what's parallel and what's not. Oh man, I wonder what that sounds like on the microphone. Goofball. Okay, 3 planes of cleavage, 90 degrees. 3 planes of cleavage not at 90 degrees is going to make this sort of rhombohedron shape. Okay, looks like that box, but someone sat on it. Okay, it's all lopsided. 3 planes, flat sides, boom, 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 but no 90-degree angles. Okay. And then finally, 4 planes of cleavage. Looks like that. It's a fun shape. I don't give you anything with more than 4 planes of cleavage. They exist, but I'm not that mean. Okay? So 1, 2, 3, 4, and there are parallel sides down here. Okay? That's what we've got. Any questions about cleavage? Just having fun playing with blocks. Appreciate that. All right. When my mineral does not have cleavage, it has fracture. There are different types of fracture. The different types of fracture that are relevant to the class, you will find listed in the Lab 1 PowerPoint. The Lab 1 PowerPoint has the same details that I've got in this PowerPoint, but with more details and more resources you can use for the lab. Okay, so remember, please use the Lab 1 PowerPoint while you were doing this lab. Quartz is a good example of this. Quartz does not have any cleavage. All of its bonds are equally strong in every direction. Quartz is just a bond between a single silicon and 2 oxygens. Equally strong in every direction, however you slice it. Which means that it has fracture. In the case of quartz, conchoidal fracture, which looks like this kind of ripply, scooped out shape right there. Kind of like if I were to take an ice cream scoop to it. That's what conchoidal fracture looks like. Density is a very legitimate measurement for studying minerals, but we do not have the time to include every evaluation technique, and measuring density for each mineral would take quite a bit of time. So I have not included that in our exercises, but I just wanted to point out, very relevant, it is important, it's not something we're going to be doing, okay? And then the other methods, you can feel free to taste things. Taste at your own risk, just don't taste 18 and 37. Texture, the way that it feels in your hand. Okay, does it feel soapy? Does it feel gritty? Like that, okay? The smell, there are going to be some minerals that have a distinct smell. I have a chunk of sulfur over there on the edge of that cabinet, that big yellow piece. Feel free to go over there and smell it if you like the smell of rotten eggs. Magnetism. Some are going to be magnetic, and you do have little magnets in your test kit to check that. And then effervescence, you do have that little bottle of acid there to see if what you're dealing with is one of the effervescent types. I will say, the only mineral that will readily effervesce, that is, it'll straight up do it without any provocation when you drop acid on it, is calcite. It's a mineral called calcite. That's really the only one that's going to unmistakably. There is one other in there, though. It's a little bit of a stinker. You got to scratch it a little bit first. Rough up the surface a little bit, or use the glass or a streak plate to remove some of the mineral and like make a little pile of dust before it'll actually effervesce. So if you're looking at it, it's like, this looks like it should be this, but I can't confirm if it is. Do that method and see if the dust will effervesce, and that'll tell you yes or no either way. Okay? Any questions about these properties? Yes?
From the games we were testing on, how come some of the bigger, not the bigger ones, but the ones that had more, why were they smaller than the ones with less? Like there was one that was bigger, and then the next one you got was a lot smaller.
That just, I mean, there wasn't really any practical reason. You mean like, oh, like why the 3 planes not at 90 degrees was smaller than the one with 90 degrees? There's not really a scale reason for that. I made those a couple years ago. It may have been just I only had so much filament decision, you know. I'm going to be remaking those at some point soon, probably with different colors, and I'll embed the magnets a little bit better. But well, that's a good thing for me to keep in mind is the scale for sure. Anything else? All right. Now let's talk about the different types of minerals. There are more than 4,000 different minerals that we've identified. We have 8 weeks. You ready? I'm kidding. You don't have to do 4,000. No, your lab 1 has 51 possible minerals on the practice set. Okay? These are all, I mean, not possible minerals. They're all minerals. Of those 51, any of them could be on your lab. You have to identify 24 on the lab, and you have a pool of 51 that they could be. So your process is basically going to be get familiar with the practice set, what those properties look like, okay, and then go to the exercise set and identify what those 24 are, right? For my online students, you're doing the exact same thing, except you have videos. You have links to all of those videos on my YouTube channel, okay? Where I do these tests and you record the properties you observe from me doing the tests on the video, okay? All right, let's talk about the way that we differentiate silicates from each other, okay? Or minerals. We do it by separating them initially into two groups, silicates and non-silicates. Silicates are based around something called a silicon tetrahedron, which I'll show you in a minute. Non-silicates are everything else. What were the two most common elements in the Earth's crust? Iron and nickel, you said? Those are the two most common in the Earth's core. What about the Earth's crust? Oh, you thought? Oxygen and silica. Yes, oxygen and silicon, the two most common elements in the Earth's crust. Bingo. Okay, they make up more than half of it. And so, any element that's based around, or any mineral, I should say, that's based around those two things is going to be a silicate. Anything that isn't, everything else. All right, so silicates are built around a silicon tetrahedron, which looks like this. Okay? It is a covalent bond between a single silicon, which has a +4 charge, and 4 oxygens, each of which have a -2 charge. So what that means is we have 4 oxygens, only 2 of which can ever be happy at a given time. Okay? Which means that they are constantly swapping out with each other, staying in the proximity of the silicon, but this overall has a net -4 charge, which means it's great for combining with certain metals that have the positive charges that would love to be attached to something with a negative charge. Okay? So when that happens, we start forming silicate minerals. Okay? Now, depending on how many silicon tetrahedrons are in my structure, I'm going to have different classifications of silicate minerals. The minerals that have single on their own tetrahedrons in their structure, we call those independent tetrahedra in the structure. When the tetrahedra start to combine together, we get single chains, then double chains, then sheet structures, and finally a 3-dimensional framework of silicon tetrahedrons. The more bound, the more complex these become, the less oxygens are needed to make the structure. So by the time you get over here, some of these 3-dimensional structures have eliminated 2 oxygens. I told you earlier about a mineral that does just that. What happens when I have a silicon tetrahedron, SiO4, and I remove 2 oxygens? What do I have? What's my new chemical recipe? SiO4, remove 2 oxygens. What does it become? SiO4 minus O2 becomes SiO2, aka silicon dioxide, aka quartz. Here's a 3-dimensional framework of silicon tetrahedrons that became silicon dioxides. It made this mineral, okay? Stay. All right. We call this polymerization, by the way. When you go from one thing to combining, binding all together, and making this far more complex structure. It's called polymerization. An example of metals bonding to silicon tetrahedrons, very simple example, a mineral called olivine, which we will go over in a little bit. Here's our silicon tetrahedron, SiO4. That's our silicon tetrahedron. What is bonded to it? Magnesium and 2 irons. Why? Because these are positive metal ions that want to be attached to this negative silicon tetrahedron. And that collectively makes our mineral olivine. Okay? So what ions do want to be a part of this? Well, irons have a +2, magnesiums have a +2, which means that oftentimes we will see them swap out with each other. There are some minerals, example of this, olivine, that will have 2 magnesiums and 1 iron, or 2 irons and 1 magnesium. They will swap out and still make the same mineral, even though there's a slightly different chemical difference, because both of these are about the same size and have the same charge. Okay? They're kind of, at least in this case, swappable with each other. Another example of this, sometimes we will see a silicon swapped out with an aluminum for the same reason. Same size, nearly the same charge. Once we polymerize enough that we can remove 1 oxygen and have an SiO3, all of a sudden, aluminum will do the job. So sometimes that'll happen and that'll mess with our chemistry a little bit. All right. Now I'm going to introduce you to some of the, what do you call it? You know, at a police station, we get a bunch of suspects and you do a lineup. I'm going to introduce you to the lineup, okay? The minerals that we're going to be going over, some of the minerals we'll be going over in your lab, okay? We separate silicates into ferromagnesian and non-ferromagnesian minerals. Who wants to guess what ferromagnesian means? Would it help if I told you it's Latin? Camera. Hello? You good? What does ferromagnesian mean? Let's break it down. Ferro. What does ferro mean? Huh? Would you like another hint? It has to do with an element on the periodic table. Namely one Fe. Huh? Iron. Yes. Fe is the periodic table element for iron, or the designation for iron. Ferro means iron. Okay, so ferromagnesian. What must magnesian mean? It doesn't have to do with magnets. It's a good guess, though. If ferro means that there's iron in a thing, magnesian must mean there's something else in there. What element might that be? It's magnesium. Yeah, it's the element magnesium. You guys ever played with magnesium? No? No Boy Scouts in the room? No Girl Scouts that played with fire? No? Oh man, we used to play with magnesium all the time. Magnesium is an extremely flammable metal. Put enough heat on it, it'll light up like a firework. Okay? So, ferromagnesian means silicates. It's a classification of silicates that have a lot of iron and magnesium in their chemical structure. So what do you suppose non-ferromagnesian means? It doesn't have that. Exactly. So we've taken our silicates and we've broken it down into 2 groups, ferromagnesian and non-ferromagnesian. Other words that we use to describe these 2 groups, ferromagnesian are usually darker colored because iron and magnesium make darker colors. Non-ferromagnesians are lighter colored. And so we have light silicates and dark silicates. That's another way of thinking about it. Just remember, light silicates, non-ferromagnesian. Dark silicates, ferromagnesian. Okay? All right. Let's talk about some of these. Right off the top, single tetrahedron minerals that form olivine. We already heard about this one. We saw its chemical structure already. That's what it looks like. It's this beautiful, lovely green color. I'll show you some in a bit. Okay? Next up, we've got a single chain. We're starting to polymerize as we go down this list. Okay? Single chain, dark silicate, ferromagnesian. This is called pyroxene. Okay? Then we have our double chain, amphibole. Then we have our sheet structures. Oh, we're transitioning now. We have our first sheet structure of biotite mica, and another sheet structure. But what's changed? What's different? It's a light silicate now. Non-ferromagnesian. Now, going further down, we have feldspar, an extremely common mineral. Okay? Light silicate. Then down here, way down here, quartz, our last one. This is going to make a lot more sense later on when we talk about magma, but I'm going to add something on here. When our magma is cooling off, as we are losing temperature and bonds are starting to form, the first thing that forms is those silicon tetrahedrons. As more energy is lost, those tetrahedrons will bond together with each other, and that's when polymerization happens. So, I'm going to add here a scale of decreasing temperature. You're going to thank me for that later. It's going to make sense. It's all going to come together. Okay? Just remember that. As temperature decreases in my magma, I'm going down this list of what gets made. All right. So let's talk about each one of these. Starting with the light silicates. Feldspar. Feldspar makes up a very, very large component to the Earth's crust and our mantle. Okay? There's a lot of feldspar in both. So and there are lots of varieties of feldspar too. Lots and lots of varieties. I'm going to be teaching you about 2 varieties of feldspar in this class. Okay? It has 2 planes of cleavage at 90 degrees. I actually have a few here. I'm going to pass around. I'm going to show it to the camera first, then I'll pass it around. I'm going to show you an unbroken feldspar crystal and a broken one. So you can see what the cleavage looks like. Come on, camera. Follow me here. Okay. This is unbroken feldspar. Ooh, almost dropped it. And then this is what it looks broken. 2 planes at 90 degrees. You can clearly see the 90-degree angle there. You can clearly see those broken surfaces, but are still flat. Okay? All right. There are 2 types of feldspar you're going to learn about. Potassium feldspar, also known as orthoclase or microcline, and plagioclase feldspar, also known as calcium or sodium feldspar. Okay? The colorations of my feldspar are going to be mostly determined by which type they are. If there's calcium, if there's sodium, if there's potassium. Okay? That's going to be a big factor for the color. Potassium feldspars, you'll often see them as pink. That's what I'm passing around right now. Okay? Pink feldspars. They can also be found as a bluish variety we call Amazonite. It's very commonly used in statues and carving and things like that. Then you have plagioclase feldspar, which has a lot of different types of color. But the easiest way to tell them apart, do you make a cleavage monster out of my models? The easiest way to tell them apart is that when you're looking at the cleavage planes of plagioclase feldspar, there are going to be lines that you can clearly see, grooves that run parallel to each other along the cleavage plane. So when you're looking at those cleavage planes and you're kind of reflecting them in the light, you'll see which kind of feldspar is this? I know it's feldspar. Which one is it? All right, I see those grooves. It's plagioclase. I don't see those grooves. It's potassium. That's how you'll tell them apart. For those of you watching the videos, I do shine light on those cleavage planes. So if you pause the video at various moments, you will be able to see whether there are grooves on those cleavage planes or not. Okay. Next up is quartz. Quartz's mineral structure, its chemical structure, is entirely silicon and oxygen. But it has a ton of different colors. What produces colors in quartz? Amethyst is a kind of quartz. It's purple. Tiger's eye is a kind of quartz. It's orange and brown. There's rose quartz, that's pink. Milky quartz, that's white. Smoky quartz, that's gray. What makes all of these different colors in quartz? They're all the same chemically. It is the light that passes through them, but it's not the light that's making the color. It's the things inside of the mineral that's reflecting the light at those wavelengths. Yes. Namely, in things like amethyst, there's a little bit of iron trapped in there. It's not part of the chemical sequence. It's not SiO2Fe. That would be a different mineral, right? It's SiO2 parentheses Fe, which means it's not attached, or at least it's not chemically attached. It's just kind of stuck in there. All right? That purple in amethyst, that's from iron. The pink in rose quartz, that's from potassium. The white in milky quartz, that's from a little bit of calcium or maybe sodium. The gray in smoky quartz, typically because some uranium was in there at one point or another. It's probably broken down already, but the radiation caused it to turn that gray color. Okay? Something is in there that has changed the color without changing the chemistry. Still SiO2, just different color. Okay? We call those inclusions. Okay, then we have muscovite. Muscovite is a single plane of cleavage, one plane of cleavage, which is why, as you can see, it breaks apart into these sheets. Okay, like pages of a book. It has that pearly luster. It's very soft mineral. It's like a 2 on the hardness scale, if I remember correctly, 2 or a 3. Okay, ladies, how many of you have glitter in your makeup? That's muscovite. Almost all glitter in makeup is crushed muscovite. Okay? Because it has that lovely luster and it's very soft, easy to break down into those tiny flakes. Okay? When minerals break down due to forces occurring on the surface, weathering, erosion, things like that. Weathering, erosion, and things like that, you will get what we call secondary minerals. An example of that is clay. Clay minerals are very common up here on the surface. We will spend more time talking about them in week 3. Week 3, I believe, is when we talk about them more. But it's the product of what happens when minerals, like what we've already talked about, break down. Clay is the most of the product, or is most of what makes soils, okay, for growing plants and such. How many of you like milkshakes? I hope I'm not about to ruin milkshakes for you guys. You ever wonder how they get the right consistency? How somehow, even though it is really cold, it stays liquid. And then when it warms up and it melts, we call it melts, so where your milkshake melts, right? It's still that thick. How come it doesn't run into a soupy sort of watery stuff? They put a little bit of clay in there because clay absorbs water. Okay, so that consistency is from a tiny bit of clay that they mix into the milkshakes. Okay. Then we have our dark silicates. Okay. Now our dark silicates contain iron and magnesium, which makes them denser. Remember how we learned that the oceanic crust is thinner but denser than the continental crust, which is why it sits at the bottom of the ocean, and the oceanic crust sits above the continental crust sits above the ocean. That difference in density is huge. Dark silicates make the majority of the material in oceanic crust. Light silicates make the majority of the material in continental crust. So our dark silicates, olivine. I have a lovely rock over here called peridotite. It comes from deep in the mantle, under the crust. See that green and black stone in there? That is peridotite. The green gems in there, that is olivine. It's probably the prettiest rock, in my opinion. I love that shade of green. It's my favorite. Okay? But olivine is among the first minerals that forms. It's actually the first mineral that forms as magma is cooling off. It's right at the top of that list, right? We estimate that peridotite like that makes up about 50% of the mass of the mantle, okay, underneath the crust. The little black gemstones you see there in there with the olivines, those are pyroxenes, which are the next minerals that form as we're losing temperature. Speaking of which, here is the pyroxene. Okay, pyroxene is easily confused with the next thing I'm going to show you. I'll just bring it up. Amphibole. Pyroxene and amphibole are often confused with each other, I will say. They are often dark or black. Amphiboles can sometimes show up as a green color. But the easiest way to tell them apart is cleavage. Pyroxene will have two planes of cleavage at 90 degrees. Amphibole We'll have two planes of cleavage, not at 90 degrees. So if you're confused about which one it is on your lab, look at the cleavage planes. If you clearly see an obtuse or an acute angle, you're looking at ampole. If you're clearly seeing something that looks like it's at 90 degrees, you're looking at a pyroxene. Okay? And this is why paying attention to each property is important. Yeah? Yes, of course. Okay. Then we have biotite. Biotite is a sheet silicate, just like the muscovite mica was, the makeup one, right? Except this one's dark color. It is a dark silicate, right? It's on the other side of that transition from dark to light silicates. Then you have garnet. Garnet is, I like to think of garnet as more or less a trash can mineral. When you are forming minerals, you get a lot of leftover stuff. And as a result, a lot of that leftover stuff goes into making garnets. There are a lot of different varieties of garnet, but they can be made out of whatever's left over a lot of the time. So I have a few garnets here. I'll show this to the camera real quick. These are garnets in a granite right here. Garnet in granite. Kind of hard to say that one. But that's what they look like. Garnets are often used as an industrial abrasive. They are very hard. Okay. All right, now I gotta take a minute to talk about the non-silicate minerals. The silicates, what we just talked about, make up most of the minerals on the crust. The non-silicates make up the rest. About 8% of the crust are the non-silicates. Okay. Excuse me. Okay. We separate the non-silicates by the ion they have in common. Okay. So we have carbonates, which are bound together by carbonate ion. Halides, that includes salt. There are several different types of what we would refer to as salts. Halide, fluorite, sylvite. Okay. Fluoride isn't actually a salt, but it's in that group. Okay. And you've got oxides, which are bound, which have in common an O2 negative bond. Okay. Hematite, magnetite, corundum. Corundum you may know as by different names. Ruby and sapphire. Blue corundum is called sapphire. Red corundum is called ruby. Those are non-silicate minerals. Those are oxides. Also in the oxide group, ice. Oh, wait a minute. Now I have to be pulling your leg. Ice isn't a mineral. That's gotta be a mistype, right? That's gotta be wrong. What was the definition of a mineral again? Someone pull it up from your notes. What's the definition of a mineral? Thank you. Any naturally occurring, inorganic, solid, stop me when this stops describing ice, by the way, that possesses an orderly crystalline structure and can be represented by a chemical formula. So that's all match ice. What's the chemical formula for ice? H2O, baby. It matches all the criteria. Boom, bada boom. Vis-a-vis, ice is a mineral. Drop mic. That's why glaciology, the study of glaciers, is part of geology. Isn't that interesting? That's why we have a whole lecture dedicated to the study of glaciers in this class. Cool, huh? Share that at the dinner table when you get home tonight. Ice is a mineral. Boom. All right. Other things, by the way, included on this list, all the native elements. So all the things that prefer to bond pretty much just with themselves, okay? Things like gold, copper, diamond. Diamond is just carbon, by the way. Diamond is pure carbon. Sulfur, graphite, which is another version of pure carbon. Silver, platinum, all those things. Anything that we find on its own, typically, counts as a non-silicate mineral as well, okay? Now, many of these things, there are silicate minerals that we mine for, but most of the things on this list, actually, all of the things on this list, are things that we mine for. Okay? So let's talk a little bit about mineral resources. Mineral resources are required in pretty much everything that you possess or use. Someone name an object. Any object. Could be in this room, could not be in this room. Tape?
Table.
Oh, table. It's made out of wood that you used metal. Someone used metal to cut that and shape it and sand it. It has a plastic top. Do you know where plastic comes from, my friends? The plastic and the rubber that you take for granted in your lives, the plastic that's in everything, from your glasses to your laptop, to your water bottle, to your table here. Glasses in your clothing, glasses on your wrists, glasses on your feet. Or not the glasses, sorry, the plastic. I kept saying glasses. The plastic in your glasses, in your feet, and everything. When you get petroleum out of the ground, it doesn't look like gasoline. It looks like this. This thick, soupy, black sludge. This is crude oil, my friends. How do we go from this to gasoline? Refining it. How do you refine it? You heat it. You remove all of the impurities. Those impurities get stored somewhere. The pure stuff, that goes to your gasoline. Where do the impurities go? That sludge, that nasty byproduct, gets turned into plastic. Every piece of plastic you have in your life comes from the oil industry. So I know that there's a huge outcry against the oil industry. And for reasons there should be. There are certain aspects of the oil industry that need to be carefully regulated and watched. I am pro-oil industry, by the way. Our society would not survive without it for many reasons. One, we would lose energy of many different types. Society would collapse if we just stopped it. Also, I dare you to imagine your life without plastic. And if you could, if you're imagining a time before we had plastic, say the 1800s, what did they use instead? What were tables entirely made out of? What were all tools entirely made out of? Wood. We stop using plastic, we start chopping down forests again. So, which would you rather have? It's kind of a damned if you do, damned if you don't sort of thing. I get that. There are no easy answers. But what I'm trying to point out here is everything in your life, every product that you have, that your life depends on, ultimately comes down to a geologic resource at one point or another. Okay? So, these mineral resources, very important, not only to find where they are, requiring geologists, figure out how to get them out of the ground, requiring geologists, and figuring out how to use them effectively, which, okay, sure, there's engineers in that, but I like engineers. I just like to poke fun every now and then. Geologists exist because engineers need heroes too. But yeah, all of this comes down to geologic resources, okay? So when we have a geologic resource in the ground, we call that an ore, okay? So that's what we'll call a metallic resource that's in the ground. Any mineral resource that's in the ground and can be extracted at some point is called a reserve. We may not be able to use it right now. It could be an anticipated reserve, something that we expect we'll be able to use in the future. Maybe our technology just isn't there yet. Maybe we know it's there, but it's too deep for us to economically access right now. And here is the next big kicker. What's the economy look like? Because the state of the economy determines what resource I can get right now. Okay? For example, this is the Bingham Canyon copper mine. Okay? That's what this picture is. This is called an open pit mine. And for a sense of scale, those are mountains behind it. You could fit one of those mountains in this hole. That's how long this thing has been dug, how deep it's been dug, how wide it is. It is massive. These roads don't look big, but these roads are meant to fit trucks that carry 500 tons of ore at a time. Okay? I used to work out a gold mine, an open pit gold mine. I'll talk more about that in a minute. But the haul trucks that we had were as tall as this building and about half the size lengthwise. Yeah, the people driving it are 3 stories above the ground. Okay. Back in the 90s, I want to say, it was either the 80s or the 90s, this copper mine was facing an economic disaster. China had flooded the market with copper, dropping the price of copper around the world. When that happens, when the price of your product drops, then the cost and the cost of producing that product stays the same, your profits drop. Okay? You can't sell your product for as much, so you lose profits. So they had a choice. Either we reinvest in the mine to make our process more efficient and become competitive again, or we shut down. So they invested a lot of money. What was a lot of money at the time? I want to say it was like $100 million, which right now is just like, don't even blink at that, right? But like $100 million they invested into redoing all their infrastructure, make it way more efficient. They were able to sell prices competitively with China, and they stayed alive. And they're still alive today. They're still producing copper around there, okay? Which is lucky for us, because if they had dropped out, China would have cornered the market on copper for like ever. China likes to do that. China kind of has the rest of the world by the family jewels for a lot of resources. Okay, I know. I painted quite a picture there, but it's true. It's true. There are 17 rare earth elements on this periodic table of elements. Every single one of those, some of the rarest in the world, every single one of those has a use case in some advanced technology. Your Xbox, your night vision goggles, your smartphone, your Tomahawk missiles. At some point, use a tiny little bit, those of you that have Tomahawk missiles, use a tiny little bit of one of those rare earth elements in its processing software. China owns 98% of the world market on rare earth metals. Okay? They don't like it when other people try to compete with them. They like having everyone. Okay? So, as a matter of fact, every time someone in the US tries to open a rare earth metals mine, they drop the price of the metals so that the new mine can't afford to stay alive. Just so that they can pick the price back up after that mine closes down, right? This is something that they've done for a while. Okay, now, the price of your product determines how much of it you can get and how pure the ore you are targeting is. I used to work at this gold mine in Nevada. I worked as an exploration geologist on this gold mine. My job was to find the layers of rock that had the largest reserves of gold in it. Now, time was, you could just pick gold up off the ground and sell it. Those are long gone. We call those placer deposits. We don't have those anymore. We pretty much just mine rock and use chemistry to get the gold out of it. Okay? Cyanide leaching, it's called. You drop cyanide over the gold-bearing rock, and the gold prefers to bond with the cyanide, and so the cyanide pulls it out of the rock, and then after a few years, you collect all that cyanide solution at the bottom of your pile of rocks, and then that cyanide solution, you pass it through a separator, and you take the gold out of it, and that's how you end up with bars of gold. The bars of gold that go to the federal mints, that go to the banks, that sell such things. You go to a pawn shop, you buy a gold medallion or a gold coin. Took years to process that out of rock because of this process now, okay? Because of how long it takes, because we're relying on chemistry instead of just looking for gold on the ground. But the amount of gold in the rock I was looking for, my cutoff, 0.03 parts per million. Not 1 parts per million, 0.03 parts per million. You would need to process essentially 300 or 400 tons of rock to get an ounce of gold that big. That's where we're at. Because all of the easy, high quality, high concentration gold deposits have already been used. So this is where the economy comes in. The demand for gold hasn't dropped. If anything, it's grown because gold is needed for advanced technologies. It's a very reliable conductor, better than copper. So, because the market has increasing the price of gold, it has become more economical to target the lower concentration values of ore. And that's how the market works. Prices increase, it's more worth it to go get the lower concentration stuff. Okay, just a little bit of insight into the economic geology sector there. All right, any questions about today's lecture? No? Okay. Then we're going to move into lab time. Before I turn off the recording here, I want to share a resource with you all. When you go to your Lab 1 PowerPoint, get back to that. Here we go. When you go to your Lab 1 PowerPoint, you're going to see a whole bunch of information on there. But when it comes to crystal form, let me just breeze through this real quick. I'm not going to spend too much time on each slide. Have you guys ever seen Journey to the Center of the Earth with Brendan Fraser? No? Oh, it's great. It's like early 2000s. I want to say it was maybe, not early 2000s, maybe, gosh, it was like 2007, 2008? Something like that. But this is a great part. Probably my favorite part in the movie. Let's see if the sound is on. Yes, it is. Okay, so for reference, they're lost. They're walking through a volcano, okay? And Brendan Fraser plays a geologist. This lady is just their guide, a cave guide. And Brendan Fraser's son is there. So only Brendan Fraser is like familiar really with, he's the geologist. So catch this. I don't know if you could hear it. Yeah, here, let's play that again. The two non-geologists are like, look at all these gemstones, and the geologist is like, feldspar. It's like, it makes half of our crust, right? This is like, it's so true. All right, moving on. Okay, so all of this stuff here, this is a very important slide. Crystal form, hard to figure out when you don't know all the shapes off the top of your head, right? I give you something to help with that. This is a website that you can follow, and it will take you here. And here you have rotating three-dimensional shapes of every possible crystal form you could be looking at. Okay? So what's your step here? To identify crystal form or shape, have it, they're all the same thing. Okay? You're going to count the number of unbroken geometric shapes. Remember, cleavage faces are the flat broken ones. The flat broken ones. Crystal form is going to be the unbroken geometric shape. So count the number of sides on your unbroken geometric shape and come here, be like, okay, I'm looking at something with 6 sides. Okay, well, which one of these does it look like? Boom. Is it that one? Boom. Is it that one? That's your process for crystal form. Okay? Another good rule of thumb here. Because crystal form, finding an answer for crystal form requires you to have enough unbroken surfaces to figure that out. And because cleavage requires you to have broken surfaces to figure that out, you are at times going to have a situation where it's one or the other. But you will always be able to get one. You won't always get both, but you will always be able to get one. Okay? It's either too broken to tell this, but you can get cleavage, or not broken enough to tell cleavage, but you can find the crystal form. Capiche? Great. All right, let's see. Rolling through the rest of this PowerPoint here. What else? Cleavage, 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 hardness, color, streak, luster. These are just examples of luster. Here's your vitreous or glassy luster. This is what pearly luster would look like, so like your micas. Resinous. This is orpiment and railgar. This is an arsenic sulfide. What resinous basically means, it looks like dried tree sap or something, right? Or old chewing gum, something like that. Something like a sticky substance that's solidified is what that looks like. Silky, looks like silk. Greasy, looks like someone sprayed it with Pam, right? Earthy, looks like it's covered in dirt. That's just what its texture is, okay? That's its luster. And then there's tenacities, optical properties, we went over that, other random properties. So what's your process? Your process is going to be, on the lab, you're going to notice everything is separated by property. I used to have it separated by sample, Then they updated Blackboard to a new dumber version, so that doesn't work anymore. So I had to separate everything by property. So you're going to have 9 different sections, each of which has 24 boxes. I know, it's not fun. It's very overwhelming, but there's no other way to make this happen in Blackboard. I am exploring other technologies to do this, but none have panned out so far. You're going to go through each sample. So you're going to do sample 1 for property 1, sample 1, property 2, sample 1, property 3, so on and so forth, answering what the different properties are. Or you could do all 24 cleavages, all 24 lusters, all 24 optical properties. Up to you and your group, if you work with a group, how you want to make it happen. But this is going to be your process. It is the process of elimination, ultimately. You're collecting all the properties you observe, either through the tests that you do yourself or the ones you watch me do online. And then once you have those properties observed, you're going to go to the Lab 1 resources folder, which will be in Blackboard. Lab 1. Look at this. Lab 1, Mineral Resources Help Lab. You need to use these. I'm not joking. Okay? You're going to go here. These are the links for my online students to, and for you guys if you wanted to work on this at home, for the access to the practice set samples. And then this is the one for the exercise set. These are the ones you're actually identifying right there. This is going to be your best friend. This is a PDF, not a PDF, an Excel spreadsheet with every single property for every single sample for every single lab thing that you're going to have in this class. That is literally your best friend. Because after you have found the properties that you observed for your samples, you're going here to find a match. Once you have found a match for your properties, that's going to tell you what the name is. And if you found your properties right, it'll be the right name. Make sense? Yeah? You know what doesn't make sense? A penny. Makes 1 cent. Huh? Okay. No questions before I finish this recording then? Alright, I will finish the recording and then I'm going to hand out lab materials, yeah? Alrighty. Where's my mouse? There it is.